Well, Michael Starch, thank you so much for spending some time with us this afternoon. Tell us a little bit about how you came to get involved in space and with NASA.
So my name is Michael Starch. I work at the NASA's Jet Propulsion Laboratory, which is one of the NASA centers out here in Pasadena, California. We are managed by Caltech. We are technically an FFRDC or federally funded research center. And that means we're managed by Caltech, but we're funded by the government. And specifically, we work on NASA projects. And so it's a really cool place to work because we do things like, well, the Mars helicopter and other deep space robotic missions. I was hired here something like 10 years ago or more than 10 years ago now. And I came from the University of Michigan.
Wow, so it sounds like you get to do a lot of fun kind of projects, right? So when you talk about working on these helicopters, and I know that you do some programming as well, how could you describe to our listeners like what it's like for you every day when you go to work? You actually sound like you look forward to going to work every day.
Yeah, so that's one of those things that I realized quite recently, actually, is I actually enjoy going to work. So we'll talk about it a little bit more later, but we went to SmallSat last week. One of the first things I noticed at being at SmallSat is I wasn't at my desk doing the cool things I do every day. SmallSat was a wonderful experience. I had a lot of fun, but I also had that moment of, yeah, I also want to be back there working on my projects, building helicopters for Mars and the various other things we do. So coming to work every day is so much fun because I'm working with talented, motivated individuals who want to be here and want to build the best missions we can. And we get to solve problems that, according to the textbooks, are impossible, right? It shouldn't be possible to fly a helicopter on Mars, but we did. It shouldn't be possible to explore the space through robots, but we're doing that too. And this just makes it a job that is different every day and gives me challenging problems to solve.
That's
That's
cool.
great.
Yeah.
I want to wind the clock back a little. Now, you said you went to the University of Michigan. You graduated from there. About 10 years ago, 12 years ago, I was at the National Science Foundation, and I know the University of Michigan actually built some CubeSats. Were you aware of small satellites when you were an undergrad at the University of Michigan? And what were your college experiences like that set you on this path toward JPL?
That's a great question. And to let me regress the clock a little bit and take a moment to think. So when I was at the University of Michigan, I was vaguely aware of small sats. I was part of I can't remember the name. It was a club called S3FL, which is Student Space System Fabrication Laboratory. It was a student-run program to build various space missions. But at the time, state of the art was CanSats and CubeSats that we weren't even sure if we had a launch vehicle for because it was a little bit more than 10 years ago. I hit the 10-year mark here at JPL and then stopped counting. And I'll be honest, I didn't know a whole lot of about space at the time. What I did at university that put me on a track to NASA JPL was I was in computer engineering. I was enjoying doing embedded systems programming, but I had lots of friends around the university who worked in other programs, aerospace, mechanical, all of these places. And they came to me and said, hey, we need somebody who can write code for one of our projects. In our case, it was a research project to see if we could get a robot to climb a tether while being powered by a ground-based laser. And they needed somebody to write code. So I was like, okay, that sounds like fun. And joining that project got me involved in this space organization. And then a little bit later, I had a friend from that organization who looked at an opportunity to join NASA, essentially. It was called the Space Grant Consortium. It's a group that lots of states have to encourage students to go into space. And my friend said, you should apply for that. And when I got back was a call from JPL saying, hey, we need somebody to code for us too. Would you like to come out and work at JPL as an intern? And I said, I don't know, because I had several offers. Some of them were from tech companies that were willing to, fund me pretty heavily. And then there was this JPL offer, and I didn't know what JPL was at the time. And my friend said, you take the one at JPL. And so I took a little bit of a leap of faith and said, I will join this JPL opportunity, even though it might not be the most glamorous of the opportunities. Because again, I was in the headspace of you go work for these big tech companies and not necessarily this institution called JPL. And then I got here and looked at the sign and the greeting material at JPL, and I saw the Mars rovers. And I said, oh, this is where I am. And from that moment on, I've just been a huge fan of all the work we do. And so for your listeners, what I would take away is be adventurous. Try things that might not be what your field is telling you to do, what your professors are telling you to do. But if an opportunity sounds awesome and people outside your major or your field or your specialization are saying, yeah, this place is cool, listen to them. Because one of the biggest joys in my life is I get to work with people who do things that I can't do well. On the Mars helicopter project, I got to work with mechanical engineers. I watched a person who can solder far better than I ever could, looking up underneath the helicopter and soldering tiny wires on the inside of our electronics cube as we prepped the thing for flight. And I realized how much larger the engineering world is than just tech, just computer science, which, you know, in the computer science field, lots of people like want to go the tech route. And if that's what you want to do, more power to you. But there's a larger world out there with multidisciplinary employers. And that's where I found my personal joy.
That's fantastic. We're going to pause for just a second and do a big shout out because she has been a principal investigator and I've been many times with our Florida Space Grant Consortium. We actually podcasted with our Florida Space Grant Consortium director. So we believe in the space grant. We totally believe in their mission. And thank you for sharing that. So much to unpack here. Let's see, where do we begin?
Can I ask a quick question?
Yes, let's unpack your
a lot of our younger students, right? We're talking the ones who are just kind of moving up into the wolf pack. So we're talking maybe 6th grade, right? They, of course, and I think it's even more so of an increase after COVID, see themselves in this coding world, right? Mostly with game applications. Mm-hmm. And they know that there has to be some kind of applications in aerospace because obviously, you know, they work with Kevin. But for a student who might be listening in, wondering how those kinds of skills are used in space. I know you mentioned the helicopter. What could a typical person expect to do with a kind of a coding background when it comes to space? I mean, I know that that's tons of jobs, right? But like,
yeah, so this is one of the hidden secrets about JPL is something like 30% or more of our work is software. And so there's software everywhere in the space industry, because the thing about software is you can use it as a tool to build, you know, extensions of your own ability to understand data. You can use software to control your robots out there in space. You can use software to understand the data that the robots are sending back. You can use software to plan and manage the missions. You can use software to design the missions. And when you're working in the space field, a lot of the software is new because you're trying to do things that have never been done before. So let's use Ingenuity, the Mars helicopter, as an example, because that's a project I worked on. So I joined the project, and the first job I had on the project was to write software to test the software on Ingenuity. You don't think of writing software to test software, but when you want to make sure your software works and underneath the software, all of the electronics works, you've got to test it. And if you just do that testing by hand, you have a certain insight into how well the hardware works. But if you write software that is capable of analyzing the device as a system and testing against it, you get so much more coverage, and you get a property which is known as regression. This regression is, did anything happen in the latest version of the hardware or of the software, the electronics or the software, that broke something that worked last week? Since I'm not testing by hand, but I wrote a tool to do the testing for me, we walked through that process in an identical fashion to last week, the week before that. And so we can see very clearly when we do something in our design, build, or assembly process that changes how the system works, and we can identify it right away. The next role I had on Ingenuity was to actually start building some of the control software. So we write software that runs all of the electronics, the motors, the actuators, the radio, all of that stuff. Because Ingenuity is a robot. It goes out there. We can't get to it and press the reset button. We can't get to it and like move the rotors for it with our hands. We need to trust that it can do it all on its own. And in order to build in these processes that do all of this and orchestrate it into a flight vehicle, you end up writing a lot of software for that. And a lot of what we see at JPL is we have this custom software to run our robots because nobody's built an Ingenuity before. Nobody's wrote
Right.
a rover before. And so we see a lot of custom software that controls these electronics. And that's the job that's my job title, which is flight software engineer, an engineer that builds the software on these robotic spacecraft.
That's so interesting. I want to ask, that first job you described where you wrote software to test the software,
Mhm.
does that make you a simulation engineer, or is it called a simulation when you're writing a test for a software for the software? How do you describe that in terms of, we think about running tests on aircraft or vehicles or components, but running a test on software, how is that different from a simulation?
So that's a good question because Ingenuity also used simulations. So simulation is where you write software that mimics the system that you want to do. So we write software that pretends to be a Mars helicopter, and then we see how it behaves in our pretend environment. And the reason such things are very useful is we can't test Ingenuity on Mars until it's on Mars. How do we know it's going to work? Well, we can build physical simulations, like in our space simulator, where we pump down atmosphere and fly a engineering model, but we can also build software simulations that pretend to be Ingenuity on Mars. And those are really good for planning, seeing how the flight controller works, and especially testing off-nominal cases. Off-nominal being cases where the system might not work as expected. For example, we wouldn't want to take one of our engineering units and crash it to see what Ingenuity would do when it crashes, because then our engineering unit is dead and we can't do any more tests. So instead, we could simulate by using a fake Ingenuity what happens in an environment where something goes wrong without risking our real hardware. This is different from the integration testing or system testing that I was doing, where we're running the real software on the real electronics. And I'm running a program to automate my tests step by step to make sure they're perfectly in line. And so we use all of these techniques at JPL to ensure that we can have the best system that we get, and that one chance we get to fly on Mars works as well as we can do it. And there's
Right.
more software in as we get further in the Ingenuity process, but I want to give you another chance to ask questions before I continue on through that.
Yes, I have one. Did you run a simulation? And maybe I'm not thinking clearly, but is there enough atmospheric density such that you could have a wind speed on the surface of Mars that would cause Ingenuity to topple over? Is that a simulation you ran, or did you consider that? It's got a
That
small profile, but I'm just
Yeah.
wondering if wind speeds could be great enough that it might, maybe want to topple it over.
So the answer is I'm probably not the best person to ask on this because I'm not the helicopter dynamics person, right? I don't know everything about the flight dynamics on Ingenuity. I came at it from a software perspective. The little I do know is when we look at Ingenuity when sitting on the ground, we're fairly confident that we can survive most of the winds that Mars can throw at us. And if you look, we've been operating on Mars for about a year and nothing's blown us over yet. That's not to say that wind isn't a hazard. If we're flying, wind can be a hazard because when we're up in the air, that air current, even with the low density, can move the helicopter in ways that we don't anticipate. And we did test for that. We
All right.
did build in our simulator, our space simulator, which is a big steel can that you can pump the air down so that you're flying in a low atmosphere environment. We did build a device that pushes wind at our helicopter and saw how it actuated in the event of a crosswind. So we did test for that scenario, and we believe that we can handle most winds. But the other dangers that come with wind on Mars is it can deposit dust on your solar panel. And if you get too much dust on your solar panel, you can't charge because the solar energy just won't go through the solar panel. So that can be a concern. One of the things that JPL learned on the rovers is that wind can also help your solar panel. We planned the MER rovers. Those were the second generation of rover on Mars, the ones with the big solar panels. We planned them for 90 days because we thought we'd get dust on them and that would be the end of it. What we found is we ended up operating them for 16 years. And one of the key insights was that the wind blowing across the solar panels also helped clean it off, which meant that we could run a lot longer before the solar panels had too much dust on them to continue to operate.
And you called those MER, that's Spirit and Opportunity, right?
Yes, the
Okay.
names are Spirit and Opportunity. The program's name was Mars Exploration Rover.
Got it.
Or MER. And that's one of the things that you learn about JPL is we have internal names that we use to discuss the program while we're developing. And then we have the external name, and that external name is a challenge that we give to students to name our equipment. And so MER is Spirit and Opportunity. MSL, or Mars Science Laboratory, is Curiosity. Perseverance is Mars 2020, and Mars Helicopter, as seen on my shirt, is Ingenuity. And so
I remember those naming contests. Actually,
Yes,
some of our students
absolutely.
participated in those, and it
And-
was always like super fun, especially to get like the younger kids engaged.
Yeah.
Even some of my third or fourth graders at the time were like, "Wow, we're going to call it this," and getting them to really think about
Right.
what traits that embodies in order to kind of take on something like that.
I
Yeah.
like that because, when you work with kids, sometimes you want them to be creative. And I tell them often, I don't care what you do, but you got to have a good reason for doing it. So your naming competition is really about why did you choose that name and the backstory or the justification that kids write. I read the one from, I think it was Alabama, a student from Alabama either named Percy or Ingenuity. I forget which one, but I definitely remember that. We showed that live, by the way, when you guys landed on Mars the last time. We watched that live during the class. Very, very good times. Those are good times.
I think a lot of times too, kids have no idea, and I'm going to say even adults, right? Like I think a lot of people don't even imagine why in the world we would need to have a helicopter or something like that, on Mars or testing, those kinds of things. So in your position, do you also get to like be a part of those general ideas about what the missions are going to be, or do they come to you after, like, this is what we need and here's how we need to get there?
So there's a little bit to unpack on that question. The first thing I want to touch on is why do we need a helicopter on Mars? Because I have an opinion on that, and Ingenuity is what we call a technology demonstration. So one of NASA's primary goals is science, right? Get out there and collect science about the world and the Earth and the solar system, because that science data helps us better understand the environment that we are in, whether it be the Earth environment or the solar system environment, etc. And so exploring Mars gives us insight to a planet that is not Earth, that is different from Earth, so that we can learn more about the Earth in general, because it gives us what we call a second data set, right? A data set that was collected in a completely different environment. And so NASA's goal is to get out there, do science. That's why we send rovers and things to take scientific measurements about Mars. So the question is, why would we need a helicopter? And Ingenuity is what we call a technology demonstration. It came out of the research world, and it was to answer a very specific question. Can we fly on Mars? This is the question that we wanted to answer with this helicopter. And when we put it up there, the textbooks basically said, no, you can't fly on Mars. And we did our research and some tests and proved, yeah, there's actually a reasonable chance that you can fly on Mars, but you really don't know until you do it, until you put the equipment up there and actually take that first flight. And why is it important to answer this question? Can we fly on Mars? Well, one, there's the scientific curiosity of can we fly on Mars, but there's a much more practical reason that comes with the nature of being a technology demonstration, which is it leads to further avenues for this science that NASA wants to collect. If we remember many, many years ago, there was the little Sojourner rover that was put on the surface of Mars, and it drove around. That rover proved that you could not only do science on Mars, but that you could do mobile science on Mars. That is, you could drive around another planet and use that as a vector to take scientific measurements. And what happened right after that? Well, we sent up MER, which is a pair of rovers that Spirit and Opportunity again, and they were able to drive around Mars and take more science because they came with scientific instruments. Then we sent up MSL or Curiosity. We sent up Mars 2020 or Perseverance. And each of these stages is extending that vector of the ability to drive to take science. But there's something you can't really do with rovers, which is go into dangerous terrain. The rover is a big investment. We want it to do science. So driving it over a cliff or through an unknown debris field or something like that could be dangerous to the mission, and it would jeopardize the longevity of our ability to collect science data. That is, it would prevent us from collecting data if we crash the rover or something, right? And so we don't do that. The project managers are very careful with the rover because it is an investment. Ingenuity came in and it was a technology demonstration to fly, but what it gives us the ability to do is send up future helicopters that can fly over these debris fields, fly over cliffs, fly over unknown terrain, all in the ability to collect science with scientific instruments without the hazard that the terrain presents to a ground-based platform. And that's why technology demonstrations are so important, is because they get us out there and they give us new ways to collect science such that we aren't limited by the old ways of collecting science. And it gives us new insight into the problems that we want to solve every day.
Yes.
Science fair project
It's
every
outstanding.
day. How
Two
exciting.
things I think about. One, your Ingenuity was like a secondary payload on the primary mission. So to me, it was like a CubeSat. There's always a rocket going somewhere doing the main job, carrying the main payload. You guys built a form factor that was so small, so compact that it got a ride along, right? Perseverance carried it under its belly. Here's a question I have, and maybe there's an answer out there. Have you ever listened, and does Perseverance have the ability to record the sound that Ingenuity makes while flying on Mars?
Okay, so this is digging up some old knowledge from a while back. I'm fairly certain that Perseverance has a microphone, and I'm fairly certain they attempted to record the helicopter. This is my recollection. And so I would recommend you double check, do a Google search. If we did that, the recording will be out there. But I just can't remember because we've done many missions at NASA JPL, and sometimes I forget things, So
I feel like it did. I feel like I remember
I was trying
listening
to,
something.
maybe I'm having
That's
a partial
probably why
memory.
you're thinking it, because I think that is the case.
I'm fascinated, by how much I had no idea JPL did so much software, right? May I ask this? What was the once Ingenuity was deployed and separated physically from the umbilical from Perseverance, tell us in a very quick summary for the layman, what were the initial sequence of events for Ingenuity to turn itself on? Was it based on a timer? Did you say we're only going to turn it on in daylight? Can you share just a little bit of the ConOps of how Ingenuity first turned itself on when it was deployed on the surface?
Sure. So the deployment of Ingenuity was we drop it onto the surface, we cut that umbilical cord, as you said, and that started a timer. And after a certain amount of time, Ingenuity was planned to wake up and start communicating. This is what we call what we like to call an alarm clock internal to the project. And we had the same timer running on the rover side and as part of our Earth Ops team, so we knew to wake up and listen for the radio. And Ingenuity's job was to just say, "Hello, I'm here," and that was it. Then it would put itself to sleep, and we'd wait till the next day. The reason we sleep the helicopter is it needs to collect energy with its solar panels, and so we want to make sure that it's asleep overnight. And we wanted to get that first hello to make sure that it had survived all this time, because it wasn't really chatting with us when we were flying through the vacuum of space. And so we were sitting there, we were waiting for the hello, and the big moment, we saw our data coming in, and then suddenly we saw more data coming in. It really came down to, hey, we see more data, therefore we know the helicopter said hello. And there are lots of reasons behind why we knew more data meant the helicopter said hello, but in short, it was just, yeah, the helicopter put data down to the ground, and we knew it was there, we knew it was alive.
Which made you more excited, when your helicopter broadcast back to Earth, or broadcast that you could see that it was powered up, or the first time it flew successfully? Or is there another moment that you would say is even better than those?
So I was the downlink lead as part of the Ingenuity project. And so that means I was on the keyboard for a lot of these critical events. And so I was sitting at the keyboard watching for the helicopter to say hello. And I was on the keyboard waiting for the helicopter to send data down about its first flight. And I will say they were very different moments, right? The moment waiting for the helicopter to wake up was a certain amount of anticipation, right? We knew the hardware should say hello. We knew it should wake up, but it was always that question of how well did it survive? So it was, I would say that was a relief moment, because it powered on, it said hello, it worked very admirably. And that was our relief moment, saying, hey, we talked to this thing, this is good, our hardware is intact. The moment at the keyboard when we saw the first flight was more of an awe moment, because this was the chance to prove this research that lots of members of the team had been working for many years. And so we were all in the room, and it wasn't a question of, does the hardware work? It was a question of, is it going to do what we had designed it to do, right? We knew the hardware should work. We knew the design was solid. Now the question is it going to fly? And so that was more of a moment when we saw those images come down of, wow, everybody in the room was impressed, because it's that first moment, that first step into this new, as I said earlier, vector for science. We are now able to fly on Mars. And that was something that was impossible up till that moment.
That's fantastic. My last question for you is this: if you could start with a blank sheet of paper, design your own mission anywhere in the solar system using any type of robotic vehicle, flying, crawling, swimming, whatever, what would be one item that might be on your list, or one location?
That is a very challenging question to answer, because there are so many cool locations out there, right? We've got Venus, which is this planet that is super warm, and putting landers onto it is very difficult, challenging problem, because it gets so hot there. But we want to know what makes Venus tick, because Mars is one direction from Earth, one way different, right? Less atmosphere, less gravity. And Venus is the other direction, much heavier atmosphere, and it's a completely different environment. But then you also have ocean worlds, and those are places where we might detect life or something else on those ocean worlds, because they've got water. And what's the thing that Earth has that seems to make life tick? Water. There are moons that have volcanism, that spray lava into the cosmos. There are missions going to what we call a metal core asteroid, which is a big hunk of metal floating out there in space. There are all these places that we actively are in development with missions to go to. And there are so many places and so many environments that would be so cool to look at, and we're just unaware that they're even there, because we haven't gotten close enough to say, oh, that's there. One of the cool things that what happened in my career is we had sent a spacecraft to go out and orbit around Saturn, right? And we're orbiting around Saturn, and we're detecting science. And I wasn't on this project, so I might be a little loose with my facts here. But we're orbiting Saturn, and we go through a cloud, and they detect the chemical signature of the cloud, and they're like, wait a minute, that's water. Somebody spraying water into the Saturnian system. So we orbit again, and we notice, I believe the name of the moon is Enceladus, and Enceladus is exhibiting, and for those of you listening, you should definitely fact check, because I'm remembering facts, but I may be a little inaccurate. And so this would be a good thing to double check. But what we found there was Enceladus has a function known as cryovolcanism, where the weight of ice presses down on the water, causing the water to liquefy and then shoot out of geysers, essentially. And so what you have is a volcano made out of ice, spraying water up into the basically the system around Saturn, where the moons and the rings are. And our Cassini spacecraft was able to detect that. And we had one of those, we did not expect that moments. And now suddenly there's a new environment to go explore, right? This water geyser on this moon. And so there are all these places out there. And the more we explore, the more we find there is to explore. So it's one of those things that I can't tell you where I'd want to go, because by the time I got a mission up there, there'd be somewhere else I wanted to go. You know what I mean?
Right.
Yeah,
And
well, it
so
just reminds me of like the hero's journey, right? Like when as a literature teacher, right, I was immediately thinking, oh my gosh, it's like the Scylla and Charybdis, in the Odyssey, where you have to kind of navigate and you see all these kind of like mythical kind of places that you now get to, research from a scientific aspect. That's
Yes, I hope this is just the first of many conversations we can have. I very much enjoyed our conversation.
Well, we always end with kind of like, the advice question, but I want to know something about you before we get to that one. Something about like your when you're working, obviously you get these cool projects to work on. How much of your time would you say that you're working independently, or that you have to work with larger groups?
that's a good question. So it kind of depends on the project, right? Some projects are very collaborative, some projects are very independent, and some projects need a little bit of both. So in thinking, not in specific terms of my day-to-day, because it changes every day, what I'd recommend is build in your habit and learn to collaborate with people, right? When you have the opportunity to work on a project team, don't treat it like, hey, this is my piece, I'm doing just this, but learn how to collaborate and design with people. When we write flight software, one of the things we always try to do is what's known as a code review. Even if I wrote the code, I want other people looking at it and making sure it's the best code that we, not me, but we as a team can make. And this kind of collaborative enthusiasm where we may be working independently for a while, but we always know that there are other engineers helping, willing to offer guidance. That's one of the things I love about JPL as an institution, is we bake that in. And so I was pulled in as a collaborative engineer for things that are well outside my field, like, hey, can you talk about the electrical system, or double check this person working in the electrical system, right? What's known as the buddy system when we're doing measurements. And this is all with the spirit of one person is not quite as capable as two. And if we work together, we can really succeed. And so as thinking forward for your students and the people listening, build this habit of collaboration. Look for ways that you can work with other people and learn to work with other people, because that's what makes us strong.
I always end with the last question about words of wisdom. And I know that you had mentioned not only that working with the teams here, but also how you had mentioned earlier, take advantage of opportunities. In our final words, is there anything else that you feel that you want to share with us, that either about what you love to do, or how our kids can kind of follow your path?
This is one of the hardest questions, because advice for what people can do to follow in my footsteps is as unique to the individual you're advising as to the individual who's providing the advice. So the first advice I would say is, what I say might not fit everybody's experience. And so take it with a grain of salt. Think about what I say and see if it fits into your path through the world. Does that make sense? And that's just because, what I say worked for me, but I'm not you. Maybe taking something I say and changing it a little bit will work for you. So as I've given general advice, I very much did well working with these multidisciplinary teams. That may work well for some people, but it may not work for others. In general, I give the stock advice. Find something that you're very passionate about. Work at JPL can be challenging. We're trying to solve problems that nobody else has solved before. That can mean a lot of, might mean late nights. It might mean very difficult problems to solve. And one of the things that gets you through it is when you love the work you're doing and you're so excited about, say, in our case, space exploration, that it helps you get through those problems. It helps you get through the days where I'm looking at a line of code and I'm just like, it's not working and I don't see why, know what I mean? So passion helps. And for some people like me, finding a passion was very important. But again, that's not necessarily everyone. I very much did well in my story by working with project teams. So a way to get into something hands-on. So your program is awesome because you're actually building satellites. It's outside of the standard curriculum, if I understand your program correctly. And that allows these students to get an experience that they might not otherwise have. I benefited from programs like that where I was building things. Another thing that I benefited in my life was personal projects. One of the reasons I'm in flight software is because when I joined JPL many years ago, I started in a different section, but at home I was tinkering with little microelectronics and programming software for these things. And that has come back to help my career because I've demonstrated and built those skills when I was functioning in a job that didn't require them, but it was for the job that I really wanted. Does that make sense? And so,
Absolutely.
Yes.
Yeah, no,
Yes.
I knew, like, I really enjoyed, and I know we opened up by me kind of sharing with you that I'm the layman, but you had me the entire time just because you are so enthusiastic about what you do. I mean, it's clear. I think most people are envious when they meet people like you. People love going to work every day. So just thank you for taking some time to share that enthusiasm with our listeners.
as a closing remark, I like doing this kind of discussion and letting my passion shine because I am very grateful for the opportunity to do this work. And I'm very grateful that I have a job that I really care about and that I am really passionate about. And not everybody has that opportunity. Some people aren't working in jobs as cool as what we do at JPL, or many people working in jobs that are as cool as JPL, but they're not JPL, right? And so I get to share that passion and I get to share the love of my job in hopes that other people can share in it, even if they don't specifically work here. And so that's one of the reasons why I'm glad to have this opportunity to share something I'm passionate about, because I know there are a lot of people out there who are super excited about space, and hopefully they learned something. Hopefully they got to share in my joy for what I do.
Well, I definitely did. So thank you for that.
Thank you. We really enjoyed our time. Thank you for spending a little time with us today.
Of course.